Evening all, and welcome to our live seminar for our chemistry exam, which is for OCR Gateway. And the exam we're looking at tonight is C1, C2 and C3. So hopefully you've noticed the fact I've slowed the chat right down, because apparently in the biology one, people just prefer to type random comments rather than actually focusing on some science, which distracted some students. So you've got a time limit now, which means you're not going to be spending all of your time, hopefully, wasting time with messages, and they can therefore just focus on a bit of science for your exam tomorrow morning. So what we're going to do is we're going to go through and have a little look and see all those different bits of chemistry. We've got an hour and a half to go through this, so hopefully we'll be able to cover absolutely everything you need. If obviously there is something you do want to go through, you can post it in the chat, which I've got in the bottom window there. And hopefully we're actually not going to have it dropping out, as I've tried to cut any disruptions from the actual house today. So fingers crossed. Okay, first thing then, looking at C1, we start off with looking at particles. And one of the key things we have here is what's called the particle model. So in science, we use these models as a way to actually try to solve problems, to make predictions, and to also try to develop our scientific understanding, particularly where we're looking at things that are actually quite hard to show with actual physical entities. So when we're talking about the particle model, then we're describing the arrangement of the particles and their movement in those different states of matter. So what we can actually do with that particle model is we can actually sit there and then we can use it to explain those key properties of substances. So we can use the particle model to explain why we can compress a gas, but we can't compress solids or liquids, because in the particle model, we know there are spaces between the particles in a gas, but not so between the solids and the liquids. So hopefully we do remember that when we're looking at our particles, then this is how we're going to draw our little particle model. So solids at the top, all nice, neat rows, nice and close together, all touching. Then we've got our liquids, again, very close together, touching, but not in a regular arrangement. And then the gas at the bottom, which is in this random, very spaced out arrangement. So what we actually find is they could very well give you a table with some information about those different states of matter. So when we're looking at our solid, first of all, as we've said, they're regularly arranged and they're very close together. If we're considering the movement of those particles, then they're just vibrating very gently around those fixed positions. If we think about our liquid, then these are in a random arrangement. Again, they're close together and they actually move around and flow over each other. In our gas, random arrangement again, spaced very far apart, and they move quickly in all directions. For those of you asking why this is for higher or lower tier, we're going to do higher, foundation, we're going to do the combined and also the separate sciences. So I'll tell you when it's higher and separate science bits. When we actually come to draw these diagrams for our particle model, if we're drawing a 3D image, then we need to remember there's a couple of key problems with this. So when we actually look at it, we're only seeing some of the particles. So what we find is there are some that are only partially hidden from view and some that you can't see at all because they're in the middle of that actual structure. When we come to consider the different changes that can happen to our chemicals, then we've got a physical change and we've got chemical changes. So a physical change is where we've got a change in the state of matter. So a solid to a liquid to a gas, and vice versa. Now, these are reversible changes and we're not making a new substance. So if we start off with ice, then that's just solid water. And when it melts to become a liquid, still just water. Chemical changes, though, are ones that produce one or more new substances. So these ones tend to be irreversible, and the products that we're making are very different to that of our reactants, and they have very different properties as a result of that. So what we actually find is that in our physical change, the particles are staying the same, but their arrangement and movement changes, whereas in our chemical change, the particles actually break apart from each other and then join together in different ways. For those of you doing the higher tier, you do need to know some of these limitations of the particle model. So our particles are held together by electrostatic forces, and these forces of attraction are between positive and negative charges. So when we're considering the spacing between those particles, The further apart they are, the weaker the forces are going to be, because there won't be such a strong pull between those positive and negative charges there. There are three things that our particle model will not take into account though. Firstly, the forces between the particles. Secondly, the size of the particles. And thirdly, the space between the particles. So do bear in mind that when we are talking about the particle model, there are those three things that are a limitation of it because we're not thinking about them. Everyone needs to know this bit again then. When we're thinking about the structure of atoms, then there's a few keywords we really need to know. First one is when we talk about an element, then that is a substance whose atoms have the same atomic number. That's what we find on the periodic table. An atom is the smallest particle of an element, and a molecule is a particle that consists of two or more atoms that are chemically joined together by bonds. If we're looking at the actual size of our atoms, then we tend to use the atomic radius for this. Hopefully we know from maths that the radius is half of the diameter. When we're looking at the length of a bond, that's going to be the distance between the center of two joined atoms. And what we tend to find for both the atomic radii and bond lengths, that they're typically around 10 to the power minus 10 meters. So if you see that one, just look for 10 to the minus 10 and the actual units of meters there in order to get that right. They could also write it as 0.1 nanometers, but with this big push they're now having for the actual standard form, I'd expect 1 times 10 to the minus 10 to come up. If we think about the actual structure of our atom, hopefully we're very familiar with this little diagram. So in the center, we've got the nucleus there, which is made of the positive protons and the neutrons. And then arranged in shells around the outside, we've got the electrons, which are negative. So this part here is the nucleus, and these are the shells that contain the electrons. We do need to know some key facts about the protons, the electrons, and the neutrons. So we need to know their relative mass and their relative charge. So a proton has a relative mass of 1 and a relative charge of +1. Neutron, relative mass is 1 and the relative charge is 0. Neutron, neutral. The electron has a relative mass of 0.0005 and a relative charge of -1. So make sure you do know that, because that always used to be an old favorite where they'd give you a table with some blanks on there and you had to fill in the other bits. So a subatomic particle is just proton, electron, and neutron. So it's the bits the atom is made of, hence subatomic. When we're looking at the periodic table, there are two things that they're going to include on there. And OCR are incredibly nice to you, because what you'll find is you actually have a key on the periodic table. So you don't have to memorize which number is which in the box, because if you look at the top of your periodic table on your data sheet, there's a lovely little box that has a key that tells you what everything in there actually is. So very nice and kind of them to do that for us. We do, however, need to know what those words mean when we see them. So the atomic number, first of all, tells us the number of protons or the number of electrons in an atom, because the protons and the electrons are the same. So if you've got an element with an atomic number of 7, it has 7 protons and it has 7 electrons. The mass number is the number of protons plus the number of neutrons. So if you're asked to work out how many neutrons something has, you just do the mass number minus the atomic number. When we're looking at an isotope, then we need to know this definition. It's an element with the same number of protons and electrons, but a different number of neutrons. So make sure you know that, because it used to be a 2-mark question there. You'd get 1 mark for saying that it's an element with the same number of protons and electrons, and your second mark for saying that it's got a different number of neutrons. So the key thing here is that the atomic number is the same, because that's the protons and the electrons, but the mass number is different because that incorporates the neutrons. If ever we talk about an ion, we are talking about a charged particle. So when we're looking to see how ions are formed, then it's all about, are they gaining or losing electrons from that atom? So if we're gaining electrons, then the ion has a negative charge, because an electron is negative. So if we add an extra one, then it makes it negative. If we're losing electrons from our atom, then the ion ends up with a positive charge because there will be more protons than electrons. The next bit we need to know are some names of scientists, because we need to know how we actually came up with this final structure of the atom that we're very familiar with today. So there are 4 key groups of scientists we need to know here. First one, John Dalton. He came up with this idea that all matter is made up of atoms. So all atoms of an element are identical, and different elements contain different types of atom. Nothing that we don't already know today is true, which is good. And he actually described these atoms as tiny indestructible spheres. So Dalton was tiny indestructible spheres that's basically making up all matter. Second scientist is J.J. Thompson, and what he actually did was discovered the electron. So he carried out these cathode ray experiments, and he found that the beams actually changed direction in magnetic or electric fields. So he came up with the idea that these cathode rays were these tiny negative particles, which he called electrons. And then he came up with this model of an atom, which was described as the plum pudding model, because that was a very popular dessert going back to his time. And what it actually said was we've got all of these little negative charges scattered around a positive cloud, just like a plum pudding in his mind. Third scientist we need to know is Ernest Rutherford, and he actually worked with Geiger and Marsden. So what Rutherford actually did was carried out an experiment where he fired these beams of positively charged particles called alpha particles at a sheet of very thin gold foil. Now, if the plum pudding model had been accurate, then those would have gone straight through, but they didn't. They actually started to deflect off at different angles. So he actually worked out there must be something stopping them going through. And he actually explained those results by suggesting there's a positive nucleus that contains most of the mass of the atom, and the electrons orbit kind of like the planets. Last scientist, Niels Bohr, and he actually used these mathematical models to show that the electrons occupy these fixed energy levels or shells around the nucleus. So Dalton, tiny indestructible spheres; Thompson, plum pudding model and discovered the electron; Rutherford is the fact we've got a nucleus that's positively charged; and Bohr is the fact that the electrons are in shells around the nucleus. So that's all of C1. So there's not a huge amount in C1, but there are a few questions they could ask us around that. If we go on to C2 next, then what we actually find is we need to know again some key terms here. It's kind of an introduction to a lot of things. So what we have first of all is the relative atomic mass, which is what we look up on our periodic table. So the subatomic particle relative masses are compared to the mass of a proton. Otherwise, the numbers would be ridiculously tiny and hard to manage. Whereas the relative atomic mass, which is given the symbol of a capital A with a little r in the bottom right, that's the mean mass of an atom of an element compared to 1/12 the mass of an atom of carbon-12. Quite a mouthful, but it wouldn't surprise me if they were to ask you to write that as a definition. So relative atomic mass is the mean mass of an atom of an element compared to 1/12 the mass of an atom of carbon-12. If they ask you what the relative formula mass is, then this is the mean mass of a unit of a substance compared to 1/12 the mass of a carbon-12 atom. And what we can actually do is we can use this to actually look at the size of different molecules in relation to each other. If we wanted to work out the relative formula mass, we're adding. It's nothing too complex here. So if you've got something like sodium chloride, which is NaCl, you look at the periodic table, find Na, find Cl, add them together. If it's something like magnesium chloride, so MgCl with a little 2 in the bottom right, then that's 1 magnesium and 2 chlorines we add together to get our relative formula mass. So relative formula mass is just an ability to add up using the periodic table, so we should all be able to do that quite nicely. The next thing we come on to is the empirical formula. Something that sounds complex, it's not, okay? This is just the simplest whole number ratio of atoms of each element in a compound. So if we had something like C4H10, then what we actually do is we find the highest common factor of both 4 and 10. Hopefully from our maths lessons, we do know that that's 2. And then all you do, you divide 4 by 2, gives us 2, 10 by 2, gives us 5, and then you write down your empirical formula, C2H5. So you're just taking it down to the lowest ratio we can for each of those elements. When we're looking at purity, as I see one of the questions there, when we have a pure substance, then that consists of one element or one compound only. If it's an impure substance, it's got more than one element or compound there. If we have a mixture, then it's more than one element or compound mixed together, but they're not chemically bonded. So that's the key thing to remember, is we're not talking about chemical bonding in a mixture. Good example of a mixture is the air you're currently sitting there breathing in. That's a mixture of oxygen, nitrogen, carbon dioxide, and a range of other gases as well, but they're not chemically linked together. They're just around each other at that time. Another one that you might be asked about is an alloy, which is a mixture of a metal with one or more other elements. Might be a metal, might not, but one must be a metal. When we want to work out if something is pure or not, then what we need to do is look at its melting point. It's the simplest way. So the melting point, hopefully we remember, is the temperature at which it changes from a solid to a liquid. And what we actually do here is, if we have our substance and we put it in a bit of melting point apparatus and you watch to see when it melts, if it does so at a single temperature, then we have a pure substance. If it actually melts over a range of temperatures or a lower temperature than we would expect from a reference value, then we have an impure substance. And the greater that difference between the expected temperature and the temperature it actually melts at, the lower the purity of our compound. So the way that we can actually use this melting point is, as I say, you just heat it up, and then we can record the temperature either at regular intervals, or you then just plot a graph and you can spot the point it melts. Couple of key things here. One, make sure you heat it slowly, because otherwise you're going to miss the melting point. And secondly, you need to stir it as it melts to ensure that it's all distributed throughout the sample, rather than having one little hot spot and cooler spots. The next bit we come on to, which is a big chunk of C2, is looking at the actual ability to separate different chemicals from one another. Now, this could very easily lend itself to the 6-mark question, because they can give you a table with some information about different chemicals and then ask you how you can separate all of the different chemicals there. So it wouldn't surprise me if this comes up as a 6-marker, but again, who knows these days. So we need to know a few keywords. So solution, solvent, solute, soluble, and insoluble are the 5 key terms we need to know. And some of this is going back to Key Stage 3, which should be quite nice. So the solution is the solute dissolved in the solvent. The solvent is the liquid that does the dissolving. The solute is the solid that will dissolve. If something is soluble, means it can dissolve, and if something is insoluble, doesn't dissolve. So if you bear those words in mind, it's going to help you out with the separating techniques. So what we actually have as our first technique is filtration. So if we've got an insoluble solid and a liquid together, we use filtration to separate them. So what we're going to have here is just our little setup for filtration. Quite nice and easy. You've got your funnel with a piece of filter paper inside, and then that's resting in a conical flask or a beaker. As long as you're using a scientific word here and not something weird like a cup, then you'll be on the right tracks. And then you pour your mixture in the top here. The solid is going to sit in the filter paper and only the liquid goes through. So that means that we can separate that insoluble solid from the actual liquid there. And the reason we can do that is that the filter paper has these microscopic little holes in it that allow small molecules, the liquid, to go through, but not the larger ones. So obviously one way that we can improve the efficiency of filtration, as if you've actually sat there and tried to watch this, then it's a very slow process if you're watching just water trickle through a piece of filter paper. So we can actually improve the speed of that by fluting the filter paper. So you fold it up into this little fan shape, and that increases the surface area, therefore makes it faster. Second one that we can use as a separating technique is to separate a dissolved substance from a solution. And the way we do that is through crystallization. So what we're going to do with this is, we've got our little setup with our water bath here, and then we put an evaporating basin on top. So the reason that we set it up like this, as opposed to just chucking your evaporating basin on your tripod and heating it on the blue flame and watching everything spit out everywhere and just make a general mess, is that this is going to allow us to bring it to that temperature at which it's boiling nice and gently. So we're not getting all the spitting everywhere, it's nice and safe, and it also means that we get it to that saturated solution quite nicely. So the crystallization method actually requires it to be heated gently until we get to that saturation point. So we've evaporated off quite a lot of the solution. Now, when we've got a saturated solution, that means no more solute can dissolve at that temperature. So the crystals start to form there. Now, as that solution then cools further, then the solubility decreases and more crystals will form, which is quite nice. So you probably did this in class where you started heating it and then you probably left it on a windowsill and maybe forgot about it for a few weeks. So what we then have left in that evaporating basin are just the crystals. If you've still got some solution, just pour it through some filter paper and then you can filter it out to get it away from the remaining solution and take those crystals on the filter paper, put them in an oven just to dry them out. So that's our second technique, crystallization, separating a dissolved substance from a solution. They're not necessarily just going to give you a case of, we have a mixture of sand and water, how are we going to separate it? A little bit easy. They're probably going to give you 3 different things to separate out. So you might have something that's an insoluble solid, along with a dissolved substance and a solution that you need to separate. So just think about the logical steps. If you've got an insoluble solid, filter first, then you can go on to the next bit. Third separating technique is simple distillation. So this is where we're separating a solvent from the solution. So if we've got salt water and we want just pure water, simple distillation works. So we've got our little setup here. You've got your solution here, and then it's going to evaporate as we heat it, and then it's going to pass down this tube here, which is called a condenser. So the condenser actually has cold water that runs through it, and that's going to then condense our steam into our liquid, and then we collect it at the end there. So the key thing about this is that our solvent must have a lower boiling point than the solute, otherwise it doesn't work. Fourth one is going to be fractional distillation. So this is where we need to separate 2 or more substances from a mixture that are in the liquid state. So what we see with our fractional distillation, we've got our little selection of our solutions down here. We heat them up and then they come up this thing here called a fractionating column. So what we actually find is, as you're heating it, the one with the lowest boiling point will evaporate first, and then we collect it through the condenser once more. And then as we keep heating it, what we find is the one with the next lowest boiling point will evaporate, and then we collect, and so on. So this allows us to separate them out. And we see this again when we come on to C6 and we look at crude oil. Next technique is chromatography. So you've done this in some form in school, probably using paper chromatography. Not many schools are going to let you do the thin layer chromatography, but it's the same principle. So what we've got here is the setup for chromatography. You've got your bit of paper or your thin layer chromatography plate here. We then put it into a beaker with a little bit of solvent at the bottom, and then we leave it. And what happens is the solvent then moves up the plate or the paper and it drags our little sample up. Now, a couple of things to bear in mind with this. When we're talking about thin layer chromatography, the plate itself is a bit of plastic or glass with this silica or alumina powder that's been basically stuck onto the surface of it. Now, what that means is that you can then put your sample onto the powder, and then we can use that powder later. We can actually extract the samples from it. When we're actually setting up, you don't put the actual sample right down at the bottom here, because when you put it in the solvent, it would just wash away into your beaker, you'd get nothing. So you've got to make sure that your spot is actually above the line of the solvent. Now, what we find is that as you then leave that in the water or the solvent, it's going to move up the actual powder. So what we find is, number one, we've got to make sure we draw our baseline in pencil. If you use a pen, the ink will also go up, and then you've got a confusing experiment. So in pencil, because pencil doesn't run in this, and then the solvent moves up, and the actual points will be determined by the size of the chemicals within there. So the smallest chemicals move quicker, The biggest chemicals actually move very slowly. So when we take our plate out, and we do that before the solvent gets to the very top, we can calculate the RF value for each. And to work out your RF value, it's the distance travelled by the substance divided by the distance travelled by the solvent. So do go careful that if they give you just one of these little plates with a couple of little dots up here, and then there'll be something like a little dashed line along the top. The dashed line is your solvent front, that's as far as that goes. And then the little dots are going to be your different samples. So you measure to the middle of the spot and the top of the solvent line. Second type of chromatography that we encounter is gas chromatography. So this one is slightly different because we're using gases this time. So we've got our carrier gas here, which is inert, or is basically unreactive. We actually inject our actual sample here, and it changes into a gas, which is then pushed through the coil, which again contains that powder, which is densely packed, and it will slow down those chemicals moving. And then as they come out the other side, the detector picks it up and creates a chromatogram on the screen. So what we find is the smallest ones get through first, and they show their little peak, and then we get the next one and the next one. So you end up with this little series of peaks on your chromatogram. Two phrases we need to know to do with chromatography. We have the stationary phase, the bit that doesn't move, so that would be the actual powders, and the mobile phase, the bit that does move, so either the gas or the solvent. When we're looking at chromatography, we can actually use it to show if a sample is pure, because a pure sample will only have a single spot on the chromatogram. If it's impure, you'll have many spots on there. If we want to compare thin layer chromatography with paper chromatography, a few key points about it. It's quicker, it's more sensitive, so we can use smaller amounts of our sample. We have a larger range of stationary phases and solvents we can select from, and a single spot from the TLC plate can then be removed, and we can then run it through gas chromatography later, because all you've got to do to remove it is just basically remove the powder off the plate, which is easy to do. Next thing we need to consider is how we're going to select this separation method. We've had a look at a range of different ones. So if our mixture contains insoluble and soluble substances, it's dissolving followed by filtration, because the filtration removes the insoluble ones and we're dissolving it to get those soluble ones into our solution first of all. If we have a solute dissolved in a solvent, it's crystallization to actually obtain the solute, and simple distillation if we want the solvent. If we've got two or more substances in the liquid state, fractional distillation is our choice. And if we've got coloured soluble substances, it's chromatography. Do bear in mind though that what I've said, they're not going to give you just a single one in all likelihood. You're going to have to look and select which couple of methods and work out how to do it in the right sequence. So always remove the insoluble stuff first and then take it on to the next step, depending on what the other bits are. When we're considering metals and non-metals, which is our next little topic, we need to consider a couple of key physical properties. So the physical property is the one that you can actually observe or measure. So it would be things like metals are malleable, which means you can bend them without them shattering. They're obviously going to be ductile because we can pull them into wires. So think about those phrases that we have encountered lower down the school. The chemical properties are the characteristics that can only be determined by studying its chemical reactions. So this would be things like the metals and non-metals react with oxygen to make oxides. It's if we dissolve them in water, then metal oxides produce an alkaline solution, whereas a non-metal oxide makes an acidic solution. When we're looking at our periodic table, do remember that metals are on the left-hand side and non-metals are on the right-hand side. So make sure you know where they are, because it's going to make it a little bit quicker to find. We do have some elements on that boundary line that are actually kind of having properties of both. When we're looking at it, the horizontal rows, so the ones going across, those are the periods, and the vertical columns, the ones going from top to bottom, those are the groups. And you will have numbers for the groups on the periodic table you get in the exam, okay? Do remember that elements in the same group have similar chemical properties, and that's all down to the arrangement of the electrons there. When we come on to consider the arrangement of our electrons, then they're arranged in shells around the nucleus. and our electronic structure actually shows how those electrons are arranged. The outermost shell, known as the outer shell, quite obviously. What we need to remember are 4 key rules for the 4 shells. First shell can hold a maximum of 2 electrons. Second shell can hold a maximum of 8 electrons. Third shell is a maximum of 8 electrons, and the fourth shell up to 18 electrons. Now, what we actually find is you're going to only need to know the first 3 rules, because anything else just gets chucked in the fourth shell. They're not going to ask you to draw anything above that. And then when you come to write the actual electronic structure, you just do 2.8.1, for example. When we're looking at the actual electronic structure, we do get a lot of information from this. First one is however many numbers there are, then that tells us what period it's in. So if it was 2.8.1, 3 numbers, it's in the 3rd period. The last number of its actual structure tells us its group number and the number of electrons in its outer shell. So in that case, 1 is the last number, therefore it's in group 1, it's got 1 electron in its outer shell. And if you add up all the numbers, you've got its atomic number. As we mentioned earlier on, we talked about ions being charged particles, and they're formed when atoms gain or lose electrons. So with our metals on the left-hand side of the periodic table, they lose electrons and become a positive ion. So sodium in group 1 will lose 1 electron and become Na+. Whereas the non-metal atoms on the right-hand side, they're going to gain electrons to become negative ions. So for example, chlorine in group 7 gains 1 electron, becomes Cl-. So what we actually find then is that when we've made these positive and negative ions, they are attracted to each other. So when we've got an ionic compound, the positive charges attract the negative charges, and that's our ionic bond. So they're strong electrostatic forces of attraction between oppositely charged ions. And when we've got this, we have a giant ionic lattice, lots of positive, negative, positive, negative, positive, negatives, just repeating over and over again. Next one is the covalent bonding. So what we actually find with our covalent bonding is that a covalent bond is a shared pair of electrons. So these are the ones that form between 2 non-metal atoms. So ionic, metal and non-metal, covalent, 2 non-metals. Covalent bonds are electrostatic forces of attraction between the nucleus of each bonded atom and the shared electrons. And again, these are strong bonds. So what we actually find is the bonds holding the atoms together are strong, they're covalent bonds, but the actual molecules themselves, those forces that are attracting the carbon dioxide molecule to another carbon dioxide molecule, those are weak. They're called intermolecular forces, which is why these simple molecules actually have very low boiling points. One of the things we do need to be able to do is draw dot and cross diagrams for these 2 different types of bonding. So in terms of the ionic bonding, first of all, if we have a look at sodium and oxygen, start off looking at the periodic table, you'll find sodium has an atomic number of 11. So 2 electrons on the first shell, then 8, and then 1 on the outermost. And then oxygen has 8 electrons, so 2 on the innermost, and then 6 on the outer. So when these actually come to make an ionic bond, what's going to happen is this electron from sodium gets transferred to the oxygen. So what we actually find is 2 sodiums have to join with 1 oxygen, because we want a full outer shell here. So we start off with this, and then when we come to draw the ions, we end up putting them into the square brackets and showing the charges. So you can see we've got one with crosses, the other with dots, and those 2 crosses that came from our sodium, we stick with the crosses. Don't mix them up. They're called dot and cross because one has to be dot and the other has to be cross. So because sodium loses 1 electron, gets a single positive charge, because oxygen gains 2 electrons, it gets a 2 negative charge. So when we actually come to write the formula for this, because we're joining 2 sodiums to 1 oxygen, then it will be Na2O. So just go careful with that one. That's about as tricky as they get. They could just give you the single one, so Na and Cl, so 1 to 1, nice and easy. If we're looking at covalent bonding, it's a shared pair of electrons. So simple one here, hydrogen, they've got one electron each, so they're sharing those electrons between them, because then they've got the full outer shell of the two. So the covalent bond, remember, just that single line. You can have them having double or triple covalent bonds. The whole idea here is they're just sharing however many electrons to give them the full outer shell there. When we're considering the different models that we can use to represent bonding, then one of the common ones is a ball and stick model. So you might have played with little moddy mods in class, those little plastic balls that you stick the little rods together to join everything. The downside to this and the limitation is the size of the atoms and the length of the bonds are exaggerated. Surprisingly, atoms aren't about that big. And it also suggests that electrons making the bond don't move. It suggests they're these rigid things. Not true. When we're using a displayed formula, which is that one at the bottom there, then it doesn't show the three-dimensional shape of the molecule. So that's the limitation of that one. If we consider our giant covalent structures, then this is where we've got many non-metal atoms that are joined by covalent bonds arranged in this regular repeating pattern called a giant lattice. And two examples of this would be diamond and silica. And we're going to look at diamond a bit later on in our carbon allotropes part. One of the things we do need to know about here in C2 that again comes up in C6 are polymers. So a polymer is made from many alkene monomers which join together. And in order to do this, they need two conditions, high pressure and a catalyst. So when they join together, what we have is addition polymerization. So we're adding the monomers together to make a polymer, hence addition polymerization. If you want to name a polymer, whatever the name of the monomer is, write the word poly in front. If they've given you the name of the polymer and ask you what the monomer's name is, take the poly away and just copy it. So if you have ethene as the monomer, it becomes polyethene. If they ask you to draw the displayed formula, then they will give you the monomer. All you need to do, copy it, lose the double bond from the middle, stick arms out the side, brackets, and a little n in the bottom right. Done. If they ask you to draw the monomer from the polymer, take away the brackets, stick the double bond back in the middle, and then you're done with that one. When we're looking at our polymers, then we need to know of two types, thermosoftening polymers and thermosetting polymers. So when we're considering the thermosoftening polymers, these do not have cross-links between them. So what we find is you've got all your polymer strands that are just kind of sitting on each other like that. So there's no cross-links at all. So these ones are actually very easy to stretch. So they're like your carrier bags. Whereas we do have the thermosetting polymers, which have the cross-links. They look kind of like a little brick wall. So what we actually find on those ones is that they're much stronger as a polymer there. Now, when we come on to the next bit, we do need to know about the structure of metals. That's our last type of bonding. So when we're looking at metallic bonding, then they quite often used to give you a question to say, describe metallic bonding, and it would be probably about 3 marks, and they give you space to draw a diagram if you wanted. So this is where we're going to have to label our diagrams properly if you want to get the marks. So what we need to do, and they're quite picky about this on the other one, so I'd expect to be pickier this time round, is they wanted at least 7 positive ions. So I always say draw 8, you're safe. So what we have is we've got all of our positive metal ions in a nice little arrangement, regular arrangement, all touching, about the same size, with little positives through the middle. And then the little dots here are the delocalized electrons. So make sure you do know how to draw that. And the only other thing you'd need to say about them to get that 3rd mark is that your metallic bond is then the attraction between the positive metal ions and the delocalized electrons. So you can get 2 marks from just drawing a diagram, 3rd mark just by saying about the attraction there. If we consider the periodic table then, we need to know a little bit about its history. So hopefully we remember Mendeleev. So Mendeleev actually came up with the basis for the modern periodic table that you will be using in your exam tomorrow. So he considered a range of actual evidence to put this together, Firstly, the atomic weights of the known elements. Secondly, his knowledge of any chemical reactions of the elements and the physical properties of them. So what he then did, using that information, he put together a basic version of the periodic table we use today. So rather than just doing what other people had and just putting them into groups and thinking, well, they must go there, he actually looked at them and thought, well, actually, your properties don't quite fit here, so you need to move along, and there's a gap here for something we've just not discovered yet. So he said there's an element that will be here, we just don't know what it is yet, and he was able to predict those properties. So what he did was actually very good, and now we know what he did was right. However, in his time, we didn't know about atomic number, so he was using the atomic weights, not atomic number. 1913, Moseley discovered atomic number was the number of protons in the nucleus, and that proved what Mendeleev did was correct. In 1894, we had another scientist called Ramsay, and he actually discovered argon, which was an element that nobody had ever thought existed, because this was something that's right on that right-hand side of the periodic table there. These are the unreactive ones, the noble gases. So neon, krypton, xenon, all of these, they don't react with other things. Hence, no one had actually worked out they existed. When we're looking at our periodic table, we do need to know a couple of patterns about it. Firstly, the elements are arranged in order of increasing atomic number. The atomic number is the number of protons in the atom. The number of electrons is the same as the number of protons. The electronic structure is determined by the number of electrons, and the electronic structure determines the chemical properties, because the number of electrons in that outer shell will determine how it reacts. Hence why when we come on to C4, all of the alkali metals react in a similar way there. Next one we're going to have a look at is carbon. So carbon is in group 4 on the periodic table, or the IUPAC group 14. So because it's in group 4, it's got 4 electrons in the outer shell. So it can form 4 covalent bonds. It can either form those covalent bonds with other carbon atoms or with different elements. So it's quite a versatile little chemical there. When we're talking about an allotrope, then this is the different form of element in the same state, but with different atomic arrangements. And you need to know about the different allotropes of carbon. First one is diamond. And diamond has a giant covalent structure where each carbon atom is joined to 4 others. So there's one carbon atom, 1, 2, 3, 4 joined onto it. So this is the one that basically looks like a triangle. So diamond is a triangle shape. Now, diamond itself has a high melting point, and the reason for that is because it's got lots of covalent bonds, and covalent bonds are strong bonds, so they require a lot of energy to be broken. So whenever you're asked about why a chemical's got a high melting point, it's got a lot of strong bonds that need energy to break them. Diamond also will not conduct electricity. As we've said, there are 4 electrons in carbon's outer shell, and it's made 4 covalent bonds. So all of the electrons are involved in bonding. So there are no delocalized electrons. If ever you're asked, why does something not conduct electricity? No delocalized electrons. Second allotrope is graphite, which is this one in the middle here. Oops. So what we can see is we've got these different layers that are stacked up on top of each other with these weak forces of attraction between them. So what we find with graphite is that each carbon atom is joined to 3 other carbons. So we've got 1 spare electron left over that's not used to make a covalent bond. So what we find here is that electron becomes delocalized. So that means graphite can conduct electricity because it has delocalized electrons. Graphite does have a high melting point though, because we've got a lot of covalent bonds, which are strong bonds that need a lot of energy to be broken. And graphite is also slippery, because what we find is those layers, the weak forces between them are easily overcome. So those layers can slip over each other, hence why the graphite in your pencil leaves marks on a bit of paper. Evening, Tyler. So do remember that when we're looking at graphite, we can use it, number 1, in electrolysis, as we're going to look at later on, as I know lots of you hate electrolysis. And secondly, we can use it as lubricants because it does have that slippery motion. Third one is graphene. So graphene is one that's just a single layer of graphite. Don't mix them up. So graphite, multiple layers all stacked up and joined with these weak intermolecular forces. Graphene is a single layer of graphite. Now, key things about graphene: it's extremely strong, it can conduct electricity, and is almost transparent. So what we actually find here is graphene could have some amazing uses in our future for technology particularly. They did have a question a couple of years ago about graphene being used for mobile phone batteries that charge up in mere seconds. So bear that in mind as a few key properties, because remember, one thing they are going to do is they're going to be putting things in contexts that are not stuff you've been taught about in class. So you've got to look for the key things, think, what do I know about it? Good evening, George. So last type, the fullerenes. These are a family of carbon allotropes that are either shaped like tubes or balls. So a nanotube is basically a sheet of graphene that we've rolled into a tube there, and we use these to reinforce tennis rackets. It's the great example they love to use. Don't ask me why, but there we go. The reason for that is they're incredibly strong. The second one, the Buckyball, this was always an old favourite of theirs. It's a ball shape. So it's made of 60 carbon atoms all joined together in a sphere. Now they have quite useful potential uses here, because what we can do in that sphere, we could put a drug, like a medicinal drug, that we can then target particular cells. So it's like a little cage to allow us to deliver a drug to certain cells. So in theory, we can actually use this to then allow us to use chemotherapy, which doesn't affect the whole body. It would just target those cancer cells and release the drug just to the ones it needs to. Hopefully we now have a bit of a better understanding about those carbon allotropes. Next thing we need to know about is how we change state. So when a substance changes from a solid to a liquid, we're breaking some bonds. And when it changes from a liquid to a gas, the rest of the bonds are going to break. So the stronger the bond and the more of them there are, the greater the energy transferred from the surroundings in order to break them. It's just a little bit of common sense on that one. So if we've got a substance that has a high melting point, then it's got a lot of bonds in that are strong. If we've got a substance with a high boiling point, then it's got a lot of strong bonds when it's in its liquid state. If we're looking at substances and the reason that some are brittle and some are malleable, then it's all about how easily the particles can change their positions in the lattice. So in our metals, the metal ions are held by those metallic bonds, and when we apply enough force to a metal, they actually slide over each other. So we're not breaking bonds because the delocalized electrons are free to move around them. So obviously those are malleable. We can change their shape quite easily. If we think about the giant covalent structures, then when we apply a large enough force, many covalent bonds break at the same time. The substance is going to break, so it's brittle. Same with the ionic compounds. We apply a large enough force, many ionic bonds break simultaneously, and it breaks. Thinking about the simple molecules and the polymers, if they're in the solid state with the molecules arranged in a lattice, they're quite likely to be brittle. Whereas if they're not arranged in a lattice, they're probably going to be flexible. We've already said the reason that our different chemicals are able to conduct electricity is if it's got some kind of charged particle that's free to move. So metals will conduct in either solid or liquid states because the delocalized electrons can always move. Ionic compounds contain ions, so they're charged particles, and they are free to move when they're either molten or they're dissolved. Simple molecules, polymers, any of the covalent structures, those won't conduct electricity because they don't have the delocalized electrons. For those of you doing GCSE chemistry, you need to know about nanoparticles. If you're doing combined science, you can just shut your brain off for a second. So when we're talking about a nanoparticle, these are the ones that are between 1 nanometer and 100 nanometers across. And hopefully remember, a nanometer is 1 × 10⁻⁹ meters. So a nanoparticulate is a material that's made from nanoparticles, and their properties are going to be quite different from that same material in bulk. Now, a good example of this is titanium dioxide, which is white when it's in bulk, but when it's in its nanoparticulate form, it's transparent. So their tiny sizes make them very useful for us in terms of paints, cosmetics, sunscreens, medicines, etc. And they've also got a very large surface area to volume ratio, which means they're brilliant as a catalyst, and we can use them on things like self-cleaning windows and ovens. There are some downsides, potentially, to do with our nanoparticles. They are incredibly tiny, as we've said. So that means that we could breathe them in, and it could also be absorbed by our skin or pass into cells. And we don't really know the long-term effects of that at this time. They take a long time to break down in the environment. Again, long-term effects, who knows? And toxic substances may stick onto their surface as well, which is, again, problematic in the long term. So that's all of C2 done. All we need to do now is C3. So this is the bit I know a lot of you seem to think is a bit harder and you struggle a little bit more with it. So let's go through it, and I'm sure we'll all be fine by the end. First thing, we need to know a little bit about the formulae. For those of you who want to know about the practicals, we've already gone through most of those in the separating techniques, because your practicals that are going to come up in the first chemistry paper are the different separating techniques and possibly a little bit on titration, which we're going to cover in the C3 part. So if we think about formulae then, when we write metals, we write it as their empirical formula because they exist these giant metallic lattices. We're not going to write Mg 3021. We just write Mg. It's far easier. So what we also find on the right-hand side, where we've got our noble gases, which is our group 0 there, they exist as individual atoms. So you will only find He, Ne, Ar just as individual entities. Whereas group 7, the halogens, just one in from that right-hand side, so fluorine, chlorine, bromine, iodine, astatine, those ones exist as diatomic molecules. Di meaning two, atoms, so two atoms joined together. And this is the most common mistake that my class know full well, they do my head in when they make it, that we make when we're trying to balance an equation, which is why it goes so horribly wrong. If you're writing chlorine, fluorine, bromine, iodine, and you just write it as Cl, Br, or I, you're never going to balance it right. You've thrown away both marks on a balancing equation. They always go round as a pair. So that means they always have to be written with the little 2 in the bottom right. If you're not doing this, your balancing is awful, and therefore it's never going to work. They are diatomic, 2 always. Don't forget that, because otherwise I won't be happy with my kids. Your molecular formula is going to show you, number 1, the symbols for the elements, and secondly, the number of each element that's present. So CO2 tells us there's carbon and oxygen, 2 elements, and we've got 1 carbon and 2 oxygens, so a total of 3 atoms. That used to be a favorite on the foundation, was giving you a chemical formula and saying how many different elements is it made of and how many atoms is it made of. So hopefully we can do that. When we come to have a look at the charges, there's a few we should remember here. So first of all, hydrogen ions have a +1 charge. Elements in group 1, +1 charge. Elements in group 2, +2 charge. If they're in group 3, +3 charge. And our transition metals usually have a +2 charge. But if not, then there's a little number in brackets and Roman numerals that tells you the charge on it. In terms of the ones on the right-hand side of our periodic table, the elements in group 5 have a -3 charge, the elements in group 6 have a -2, and the elements in group 7 a -1 charge. So what we find there is just by looking at the group number, we can work out the charge. On the left, it's positive, and whatever the group number is, that's your positive charge. So group 1 +1, group 2 +2. On the right-hand side, we just need to work out how many it's off from 8. So if it's in group 7, it's missing 1, so it's a -1 charge. If it's in group 6, it's missing 2, -2 charge. We also have these things called compound ions, which contain more than one element. And there are some we should know for the exam tomorrow. I hope you know these ones. So the ammonium ion is NH4+, hydroxide OH-, nitrate NO3-, carbonate CO3-2-, and sulfate SO4-2-. And the key thing that we need to know these charges for is that when we're putting them together and writing the formula, then we've got to make sure the positives and the negatives cancel out. So if we've got magnesium, which is 2+, and hydroxide, OH-, we need 2 hydroxides to each magnesium. So the way we'd actually write that give me 1 second, is like so. So we've got one magnesium because it's got a 2+ charge. The hydroxide ion has a single negative charge. So we need 2 of these to cancel out one of those. So you stick it in brackets and put the little number down there. So one law we do need to know, one that goes back to some work we did at Key Stage 3 again, the law of conservation of mass, which just states that atoms cannot be created or destroyed. So the way that they're changed, the joint changes in a chemical reaction. That's it. You've still got the same number of atoms in your reactants as you do in your products. We can't lose them. We can't create them from nothing. They don't just pop into existence. So the total mass of our reactants is the same as the total mass of our products. So when we're actually carrying out a reaction in a closed system, so one that's completely sealed off, nothing can escape, nothing can get in there, etc., then what we actually find is that you end up with the same mass at the beginning as at the end. So you can have things like beakers where we're not making a gas. However much you've got at the beginning as the mass is the same as at the end. And do remember that, because they do like to sort of give you an example where you start off with however many grams of the reactants, and they tell you you make so many grams of one product and ask you how many grams of the other. So however much your reactants are, minus whatever product you know, left over is your mass of the unknown. When we come on to our chemical equations, word equations first of all, this is mainly going to be on the foundation tier paper. You need to write the whole word. So do not get lazy and write carbon dioxide as CO2 in a word equation, because that is wrong. You will not get the marks for that. You have to write carbon dioxide if it says word equation. The balanced symbol equation, this is where we actually use the symbols, and the balanced part means we've got to have the same number of each of those elements on the left-hand side as we do on the right-hand side. So that's where we need to go through and do the balancing side of things. Good news, in the past anyway, it always used to be a 2 in front of something. So generally speaking, if it wasn't 2's in front of it, it was probably already balanced. Now, the other one we used to be able to spot was that if it was worth 1 mark, it was already balanced. If it was 2 marks, it needed balancing. I'm not guaranteeing that's going to be the case tomorrow, so don't take that as gospel, but possibly true. If it's a 2-mark balancing question, then you used to get 1 mark for writing the correct formulae. So even if you think, oh, balancing, can't do that to save my life, give up, I'm not going to even attempt that, then what you can do is still write the chemical formulae down, because they're in the question. So it's basically an attempt at copying from the question. So that means that what we can actually do is get 1 of our 2 marks quite nicely just by copying those down. If you can have a go at balancing, brilliant. They're not going to take away the marks as long as you remember that the balancing can only go in front of those formulae. You can middle or anything weird like that, only in front. The other bit we need to know about the state symbols. There are 4 we need to remember. S for the solids, L for the liquids, G for gases, and AQ for the aqueous solutions. In all honesty, 9 times out of 10 on your exam paper, it's probably going to be AQ. The ones that you will see as different, obviously, your known gases, oxygen, hydrogen, carbon dioxide, G in brackets, okay? If not, then what you're going to do is L for water. Other than that, very much doubt you're going to be asked for a liquid. And if you can see it's a lump of metal, put an S in brackets. Otherwise, if you're not certain, go with AQ in brackets. For those of you doing the higher tier, we need to know how to write half equations and ionic equations. So what we have here, the half equation, is a model for a change that happens to one reactant. So what we're doing here is we're taking an overall chemical equation, like sodium reacting with chlorine, and we're only going to look at one reactant at a time. So what we start off with is sodium plus chlorine makes, just about fit on there, sodium chloride. Just quickly balance that. So that would be our overall equation. Now, if we're writing our half equation and we only want to look at sodium, then we'd start off with our sodium and we're going to show what happens to it. So sodium at this point is actually going to lose one of its electrons. So we start off with a sodium atom, and it's going to make a sodium ion and an electron. So that would be our half equation for the sodium. If we do the same for chlorine, then what we're going to find is we add 2 electrons to it to make our chloride ions. So we start off with our chlorine gas, Cl2, group 7, remember, diatomic. We add 2 electrons, given the symbol E-, and we make 2 Cl- ions. So those are all we're talking about when we refer to a half equation. You're just looking at one reactant and you say what happens to it. If we look at ionic equations, then what we actually have is the complete ionic The complete ionic equation shows the ions present in the reaction mixture, and it will also include the formulae of molecular substances or those in the solid state. So you would have the big ionic equation, but what we actually do is we don't include spectator ions. So spectator ions are the ones that are the same on both sides. They're ones that aren't taking part in this reaction, so we don't include them when we write our net ionic equation. So what we can start off with is something that's got, if we're doing hydrochloric acid and sodium hydroxide reacting to make sodium chloride and water, then all of the ionic parts would be H plus Cl minus plus Na plus OH minus makes Na plus Cl minus plus H2O. What we got there are a lot of things that don't change. Okay, the sodium and the chloride ions are the same on both sides. So we don't need to worry about those. They're spectator ions. The only things that change from the left to the right are actually the hydrogen ion and the hydroxide ion on the left to make water on the right. So spectator ions, the ones that don't change from the reactants to the products, they start as an ion, they end as an ion. Irrelevant to us when we write our net ionic equation. So if we're writing the net ionic equation for that, it would be H plus OH minus makes H2O. So we generally use these to model precipitation reactions because we're looking at just the ions and what they're making on the other side there. Still for the higher tier only at this point, we need to know about moles. So I know this is the substance that my lot generally just turn their nose up at, grown lots, and then just bury their head on a desk, but they're not as bad as you all think. When we're talking about a mole, it's the amount of substance that contains the same number of entities, and an entity could be an atom, an ion, or a molecule, as there are atoms in 12 grams of carbon-12. So its units are mole, MOL. When we're looking at this, one of the things they could ask you to do is to calculate the number of entities. So this is not a tricky one. All we do is the amount in moles times the Avogadro constant, which is 6.02 times 10 to the 23, which they give you on your exam. You don't have to memorize it. You'll be glad about that. So it doesn't matter whether it's molecules, atoms, ions, whatever. Same thing, 6.02 times 10 to the 23 times the amount of moles. So if it's 5 moles of hydrogen gas, 5 times 6.02 times 10 to the 23 gives you your answer there. When we come on to calculate the molar mass, this is where we're just going to go on and use the periodic table. We're going to do some adding. So if we were asked to calculate the molar mass of sucrose, C12H22O11, we do 12 times our carbon, which is 12, plus 22 times hydrogen, which is 1, plus 11 times oxygen, which is 16. Add all that lot together, and we get the molar mass. Those of you doing the higher tier, then we need to know about the calculations for moles as well. This is just a case of learning one equation, and then we're going to use that one equation, rearranging it a little bit to find out whatever we need. So first thing, the equation itself, the mass in grams is the molar mass in grams per mole times the amount in moles. Learn that. When you get a calculation question to do with moles, write that down first of all, because that's your go-to equation that you need for this. So the kind of question we could get here is nitrogen reacts with hydrogen to produce ammonia, and they will give you the balanced equation if they're nice. If not, I might ask you to do it. And they'll ask you to calculate the mass of ammonia made from 84 grams of nitrogen. So first thing we do with this, and if you do nothing else on these, then calculate the molar masses of nitrogen and ammonia, of the two things you need. So that's a simple, use your periodic table and add. We can all do that, and that gets us our first mark there, which is good. Once you've got that, we've got a molar mass and a mass in grams for nitrogen. So we can use our equation at the top there, rearranged, so that the amount is the mass divided by molar mass. So 84 divided by 28 gives us 3 moles. So that would be our second mark for doing that bit. We then look at the balanced symbol equation, and we're looking at the ratios here. So in our equation, we've got 1 mole of nitrogen making 2 moles of ammonia. In ours, we can see we're making 3 moles with our nitrogen. So we've got 3 moles of nitrogen, balanced equation was 1, so it's 3 times bigger. 2 moles of ammonia were made from 1, so 3 times 2 gives us 6 moles of ammonia. So now we've got the amount in moles and our molar mass for ammonia. So back we go to our equation. Mass in grams is the molar mass times the amount. Substitute it in, 17 times 6 gives us 102 grams. So all we need to do is just sit there, go back to that one equation, mass in grams is the molar mass times the amount in moles, and rearrange that until we get to the end point. But that could well be a 4-mark question, so it's worth working your way through it. Even if you can't remember how to get to the end, you can get some of the marks. So every mark counts, as we know, and it's worth doing that. Everyone now, so hires, foundations, combines, separate sciences, back we come. So what we actually have is we need to know, let me just hide that one, the difference between exothermic and endothermic reactions. So exothermic reactions are where the temperature of our reaction mixture increases because heat's given out to the surroundings. So if you're asked how you can tell a reaction is exothermic, temperature goes up. So that would be good examples of combustion, neutralization reactions, and so on. Endothermic reactions are ones where the temperature of the reaction mixture decreases. So these are the ones that cool down. And that's because heat's being taken from the surroundings to actually carry out the reaction. Good example, as hopefully we wrote down yesterday, is photosynthesis. So other examples of this one they could ask us about tomorrow: electrolysis and thermal decomposition. Those two are endothermic, but they don't show a temperature decrease. The energy is actually used to break down the substances instead. So what we actually find, and the reason we get these, is that in a chemical reaction, we're transferring energy. So we transfer energy from the surroundings to break bonds in the reactants, so we get separate atoms. And then we transfer energy to the surroundings when those particles form bonds between the atoms. Now, what we would be asked to do potentially is to draw something called a reaction profile. And I know that a lot of my lot did not like this much previously. So reaction profiles are nowhere near as bad as they sound. It's basically a chart that shows you the energy involved. So you're not going to have to do scales and things like this. It's going to be a nice simple little diagram, a couple of lines joined by a bumpy bit. Pretty much what we're talking about here. So the horizontal lines we're drawing, those represent the amount of energy stored in the reactants and the products. And then the little bumpy bit, that's our activation energy. And the difference between those two lines is the actual energy change. So what we can see here is the energy change is just the difference between the energy we're transferring to break the bonds and the energy we're transferring to make new bonds. So when we come to actually draw these, you need to think about which direction is it going in. Are we actually putting more energy in or giving more energy out? When we refer to the activation energy, that's just the minimum energy needed for a reaction to start. So if we don't reach the activation energy, we don't get a reaction anyway, even if the particles collide. So what we actually find is we usually get that activation energy by heating things. So it breaks the bonds in the reactants. What we actually find, though, is that there are some that just by merely mixing chemicals together, they've got enough energy to meet that activation energy. When we come to draw our reaction profiles, we will end up with one of these two diagrams. Let me just close the blind a second. So what we have, there you go, hope you see that a bit better, is endothermic reactions and exothermic reactions. So our endothermic reaction, the reactants line is lower than the products line. Whereas in an exothermic reaction, the reactants line is higher than the products line. So as long as you remember that, you can then draw this. So you draw your horizontal line, for your products, and then you join it with a little bump. Same thing over here, draw your reactants, then draw your products, and join it with a little bumpy line. They're not going to be asking you to plot this very accurately. They might in A-level, but as far as we're concerned at GCSE, horizontal line, little bumpy bit to join the two together. So what we actually find in the endothermic reaction, energy transferred to break the bonds is more than the energy transferred when new bonds form, okay? Whereas an exothermic reaction, the energy transferred to break the bonds is less than the energy transferred when new bonds form. So as long as you know that, you can do those. For those of you doing the higher tier, then you do need to know how to calculate energy changes. And I know some of the Year 11s were struggling with this after school tonight, so we're going to run through it nicely for you now, hopefully. So what they can give you here is a little table that's got a range of different bond energies. So they'll give you a table that's got carbon to hydrogen, carbon to carbon, carbon to oxygen, all of that down one side. And in the second column, it will have a whole bunch of numbers, so 463s and all of this malarkey. Now, what they're also going to give you is a displayed formula of the actual reaction they want you to do. So if we had, just give me 2 seconds, a formula like this, then that's our displayed formula for the reactants. So what we need to do to actually work out the bond energies is we're going to do a counting exercise. So over here, we've got 1 carbon double bond carbon bond. So we would write down 1 times and whatever the value for the carbon double bond carbon from the table is. Plus, we've got 1, 2, 3, 4 carbon bond hydrogens. And again, so it'd be 4 times whatever that value was. And then we've got an oxygen double bond oxygen. So we would also add that. The sum total of all of that is the bond energy in our reactants. Then we do the same for the products, and all you then do is you just subtract the right hand side from the left hand side. So all you do, type in the calculator whatever you got for your reactants minus whatever it was for the products, and write down that answer. That's all we need to do for this one. Important thing to remember though is the sign. Okay, you must write down whether it's positive or negative for your answer. A negative sign tells us it's exothermic. A positive sign tells us it's endothermic. So make sure that you do cover those bits, because otherwise you're throwing away a nice easy mark there. Back for everyone again. So foundation, higher, combined, chemistry, everyone back together for this bit. Good old redox reactions. So a redox reaction is where we've got a reduction and an oxidation happening at the same time, hence redox. We've just merged the two words together. So reduction is where we lose oxygen, whereas an oxidation, we gain oxygen. So a good example of this is in the old thermite reaction that hopefully you saw in your classrooms, maybe set off the smoke alarms if you've got a new build like we do. Then what happens is in that we've got aluminium and iron oxide as the reactants, and we make aluminium oxide and iron. So what happens here is aluminium is oxidized because it gains oxygen in the reaction. So we refer to it as the reducing agent. So it's the oxidizing agent. We're transferring oxygen from iron oxide to aluminium. If you're doing the higher tier, then we need to know this in terms of electrons. So this is where we go back to our little acronym of oil rig. Oxidation is the loss of electrons. Reduction is the gain of electrons. Now, what we actually find is that in this one, if we consider our half equations, then we start off with our aluminium one. So if we think about aluminium, then we're going to be changing that into aluminium ions, which means our half equation is this one. We start off with an aluminium atom, and then we make aluminium ions, and we've got our 3 electrons there. So because we've lost 3 electrons, that means it's oxidation. And then if we consider what happens to the ion on the other side, then what we end up with is it's gaining electrons. So we start off with an ion, gain 3 electrons to make an iron atom. So we're gaining our electrons in this case, so it's a reduction. Just remember, oil rig, oxidation is loss, reduction is gain. You'll be fine on that. Back for everyone again, so higher and foundation, everyone comes back together once more as we look at the pH scale. Now, hopefully this should be a lovely question for us. I really, really hope so, because we're going back to year 7, which is a nice, happier time for us all. There were no stresses and exams and great trauma in our lives. We've got 3 different categories we need to remember: acids, alkali, neutral. So an acid, that's the ones that are less than pH 7. So they're reds, oranges, and yellows with universal indicator. So 1 to 6, that's our acid. In terms of a slightly higher level than year 7, acids release hydrogen ions when dissolved in water. That's the only real difference. Neutral solutions, they are pH 7 and they are green with universal indicator. And the alkalis are greater than pH 7, so the 8 to 14s, blues and purples with universal indicator. And what we find is that when they're dissolved, they release hydroxide ions, so OH-. If we want to measure pH, 2 ways we can do this. One, the rubbish inaccurate way that we make you do in school with good old universal indicator and that terrible little color chart where you're sitting there looking at it and thinking, this is the same as about 6 different colors on this chart. What is it? And then the far more accurate pH meter. So if they give you an example of a practical where they're using universal indicator to work out the pH and ask for an improvement, use a pH meter, because that's a digital probe. You stick it in, you push a little button, and it gives you a number on a screen. Do a decimal place usually, way more accurate than guessing colors. So what we actually do here is we need to calibrate that pH meter first of all. So you wash it, you then put it into a buffer solution, which is a known pH. Then you match that by turning a little screw on top, wash the probe, stick it in your test solution, read the screen. Done. Nice and easy. One of the reactions you would have looked at to do with acids and alkalis, going back to, again, good old year 7, is a neutralization reaction. So this is a reaction between an acid and a base or an alkali to form salt and water. So our general word equation, it's acid plus base makes salt plus water. Acids contain hydrogen ions, alkalis, hydroxide ions. Those 2 join together to make H2O, water. The other thing we've got is going to be the remainder. Whatever else was there, that joins together and we've made our salt. In terms of how we name salts, which is something we do struggle with, then the first part of the name is the metal in the base or the alkali. The second part comes from the acid. So hydrochloric acid makes a chloride, sulfuric acid a sulfate, nitric acid a nitrate, phosphoric acid a phosphate. So if we've got sodium hydroxide and sulfuric acid, then sodium is the name of the metal, and it's a sulfuric acid, so it's sodium sulfate we make. So just make sure you know those 4 acid endings, and then you can work that bit out. If we take a carbonate and mix it with an acid, then what we actually find is we will have a standard equation that we can use. So methyl carbonate plus acid makes a salt plus water plus carbon dioxide. So what we find here is this could bring in one of our gas tests, which is the test for carbon dioxide. So testing for carbon dioxide is using lime water, which goes from colorless to cloudy or milky, whichever phrase you prefer. If we do the metal with an acid, then we make a salt and hydrogen, and our gas test for hydrogen is a lit splint, makes a squeaky pop sound. So make sure you know those 2, because again, they could come up quite easily as the practical part. For those of you doing the higher tier, you do need to know about hydrogen ions and pH. So when we've got our solution, that's a solute dissolved in a solvent. The greater the amount of solute it contains, the greater the concentration. And what we actually find is we've got 2 terms we use to do with this. A dilute acid, this has a low ratio of acid to the volume of solution, whereas a concentrated acid has a high ratio of acid to volume of solution. So when we're looking at concentration, that's the amount of the solute dissolved in the solution. The second thing is we need to know about strength. Concentration and strength are not the same thing, even though so many of you like to pretend they are. They're not. So as we said, acids release hydrogen ions when they're in an aqueous solution. So what we actually have happening there is the covalent bond is breaking between hydrogen and the other part of the substance to make a negative ion and the hydrogen ion. Now, the strength of the acid is determined by how many of those hydrogen ions are released or how ionized it is. So weak acids are partially ionized, so only some of the hydrogens have split off, whereas a strong acid is fully ionized, they've all split. So just remember concentration, amount of solute dissolved in the solution, whereas the strength is about how ionized it is. Do remember where we see the little reversible reaction sign, so that one, then that's going to be partially ionized. So anything you see with that is partially ionized and therefore a weak acid. If we consider what happens when we increase the concentration of hydrogen ions, if we increase them by a factor of 10, the pH decreases by 1. So just bear that one in mind because that did come up on one of the specimen papers. Next one is titration. So another experiment that could come up on either of our chemistry papers here. Hopefully we remember the big glass tube that's stuck in that stand is the burette. We will measure the volume for our conical flask or beaker using a pipette, and that's because it's accurate. When we're actually using our actual burettes, number one, before you put the acid in it, close the tap at the bottom. Then we're going to use a funnel to actually add our acid so it's nice and safe. In terms of safety precautions they could ask for here, don't fill it above your head, as I see so many people do. You place it on the floor and fill it so it's not above your face when pouring acid into a chemical container. And we're also going to make sure that it's held securely in the clamp stand. Those should cover any kind of safety precautions you need there. Now, what we can do with this is we've got our acid in our burette, you've got your conical flask with your alkali in there, and all you're going to do is have a little pH probe in there. You write down your pH at the start, add 1 centimetre cubed of your acid, give it a little mix, record the pH, another centimetre cubed, give it a mix, record the pH, etc. And then what you can do is plot a titration curve. Now, what we'll find is you're going to end up with something that looks rather like this. Excuse my very bad drawing, but you'll end up with a curve something like that. And where we've got that vertical part, that's where it's neutralized. So you can then use that to work out the volume of your x-axis at which it was neutralized. That's probably, I say probably, all the detail they're going to ask you about titrations for tomorrow's exam. The rest of it we go into way more detail later on in our second chemistry topic. So the last bit we need to go through then is electrolysis. So the bit you will hate the most we've saved till last. Electrolysis is just where we're using an electrical current to actually split a chemical. So in order to carry this out, we need 2 electrodes made of either metal or graphite, i.e. something that conducts electricity. We need an electrolyte, which is our solution that contains the mobile ions, and we need a power supply. So what we actually have here, we need to know the names of the 2 electrodes first of all. The cathode is the negative electrode, the anode is the positive electrode. So I always tell mine to think of the grumpy cat picture. So you've got a very negative looking grumpy cat staring at you, that's your cathode. What we actually find with our electrolysis question, and this is our little setup. So we've got our 2 electrodes, the cathode on this side, anode on this side. They're connected to our power supply at the top, and they're sitting in the solution of our electrolyte here. So when we actually switch the power pack on, electricity is able to flow, and what happens is these ions, which are positive and negative, are attracted to the oppositely charged electrode. So any of the negative ions in our solution here go to the anode because it's positive, whereas any of the positive ones go to the cathode because it's negative. So opposites attract. And then as they reach the electrodes, they're going to have that ability to transfer electrons to become an atom. So what we actually find, the positive ions gain electrons at the cathode to become an atom, and the negative ions lose electrons to become atoms. Do remember that we tend to use inert electrodes for this because they don't change. So things like the graphite or copper we would use here because it's not really used up. If we're looking to see what we get formed at the different electrodes, then we need to remember about reactivity. So in terms of what's going to form at the cathode, general rule, write down hydrogen. The only exception to this will be if we have a less reactive metal present. So the less reactive metals that you need to remember, copper, silver, gold, and platinum. Unless it's copper, silver, gold, or platinum, hydrogen is forming at the cathode. So that's the nice easy one. In terms of what forms at the anode, it's going to be oxygen, unless we've got group 7 present. So if anything from group 7 is present, write that down. If not, write oxygen. So just those two simple rules means you can work out what will form at each electrode there. One of the things we can actually use this electrolysis for is something called electroplating. So we use these non-inert electrodes this time. So this is ones that will change. We actually want them to change. So what we have, the cathode becomes whatever we want to coat. The anode is the metal we want to coat the object with. And our electrolyte contains the solution of those ions that we want to coat the substance with. So when we actually turn the power supply on, those metal ions then travel across and cover the object we want to give the nice shiny plating to. So what we find there is the anode will be used up as time goes on because we're transferring those ions across to our plated object. The only other thing they could ask about electrolysis is how we extract copper. So if we've got our copper, it's not pure once we've extracted it. So we put it through electrolysis to make pure copper. So our anode is impure copper. The cathode is pure copper. The solution, our electrolyte, is copper sulfate solution. And then what happens is as the power pack is turned on, the cathode gains copper atoms and will increase in mass, and the anode loses copper atoms and decreases in mass. And you also end up with this sludgy gunk at the bottom, which is all of the impurities from the anode. Hopefully, you now have a much better understanding of what can come up on tomorrow's exam. We've gone through everything from C1, 2, and 3. So that's hopefully got you in a good position for tomorrow. Don't forget a few of those key things that we found out from our biology exam. Firstly, they will use scenarios that you've not been taught about. It doesn't mean that your science teacher has failed you miserably because they didn't teach you about some really obscure setting. It's not about the setting, it's about the science in there. So ignore the weirdness and just focus on what are they really asking me about, because it will be something you've been taught about. Also, make sure that you are reading the questions very carefully because you could very easily miss some of those tables that are needed to be filled in. We know there's going to be some kind of maths on this, it's a guarantee. You may well have a graph to draw, so remember lines of best fit, contrary to what your maths teachers like to tell you, can be a curved line of best fit. So just double check that when you're looking at all of these things, you are reading it carefully, you're taking your time, you've got plenty of time to do this, and you're answering all of the questions. And don't forget, on those 6 markers, take it one step at a time, make sure you've answered the 2 or 3 sections of the question that there may be, and you can do it as bullet points. Capital letters, full stops, that'll do. We're not a bunch of English teachers when we mark them. So just go through very sensibly, take it from the beginning and work through nice and logically. Hopefully you're all feeling a little bit more confident than you did at the start. Don't let the biology one put you off because yes, there were some interesting questions. That just means the grade boundaries will be lower. So as long as you're all doing your best tomorrow, that's all anyone can ask of you. Obviously, for my lot, 8:30 in the morning in my lab, I'll have the Mars bars at the ready and make sure you are there on time when we're just going to go through any last little bits that you need to do. Other than that, don't stay up all night revising. It won't help you out in the end. So do get an early night and make sure you have breakfast in the morning for your exam. Good luck, everyone, and we'll be back in about a week's time for our physics one.